So today I'm going to talk about locally finite matroids. So the idea is that matroid theory, or infinite matroid theory, as it is today, grew quite a lot out of topological infinite graph theory, so the theory of infinite graphs. But there are some things in that theory which only work really nicely for locally finite graphs. And so I'm going to be talking about a notion, a special kind of infinite matroid in which you can also do these nice things that you can do for locally finite graphs. So before I get on to infinite matroids, I therefore want to talk a little bit about topological infinite graph theory. And here, I guess this starts from the fact that if you take a typical fact or theorem about finite graphs, and then you just naively try to generalize it, you say, let the graph be infinite, then very often what you get is a statement which is either false or just nonsense. So I guess the most obvious example is existence criteria for Hamilton cycles. In an infinite graph, if it satisfies some criterion, so you expect to have a Hamilton cycle, of course, you won't find any cycle that goes through all the vertices because a cycle is finite. And so to try to resolve these sorts of issues, the idea is to introduce a kind of an infinite cycle in these infinite graphs, in which you're allowed to head off towards infinity through the graph, and then maybe come back in from infinity again to join it up. So let's look at an example in this graph, the one-way infinite ladder, heading off to infinity that way. And this graph will come up again and again as an example in this talk. So here, we could build a cycle, indeed a Hamilton cycle, or we could hope to by heading off to infinity that way, coming back in from infinity, and then joining up over the top, like this. And in a graph which maybe now goes off to infinity in both directions, both to the left and to the right, again, we could go off to infinity this way, come back, and now head off to infinity in this direction, and come back in. And that would give us a Hamilton cycle in this graph. So how do we make this idea precise? What we do is we take the points at infinity, the ways to go off to infinity in the graph, and these are formally defined as ends. Formally, they're equivalence classes of rays in the graph, where we say two rays are equivalent if they can't be separated by removing finitely many vertices. So they look like they're heading off the same way. And for each such end, we formally add a point at infinity, maybe over here, or one there and one there. And then, as our new cycles, we take just topological circles in this topological space that we get this way, the end compactification, mod G of the graph G. Right. And by topological circle, I just mean homeomorphic copies of the unit circle, S1. Right. Now, the situation isn't always as easy as in these two graphs down here. You could have a case like this graph up here, in which you can see that the graph kind of branches out in a tree structure as it heads off towards infinity. So when we take the ends of this graph, we're actually going to get uncountably many ends for all the infinite branches of that tree. And nevertheless, there is a topological circle which goes all around the outside of this picture and picks up all of these uncountably many ends along the way. And so you can't hope to capture this kind of behavior with a combinatorial condition, or so it would seem. Right. Okay. So what happens when you introduce these infinite cycles, and what makes topological infinite graph theory so powerful is that the statements about finite graphs, which became false when you moved directly to infinite graphs, become true again when you take references to cycles in the theorems now to refer to these to these topological circles, and you take references to paths now to refer to topological arcs in these topological spaces. Okay, so because I want to generalize locally finite graphs, now I want to talk about one result where things work nicely, but only really for locally finite graphs. And that comes from the following fact about just finite graphs. You can consider the edge set of the graph, or the set of subsets of the edge set of the graph, as a vector space, where to add two sets, you just take their symmetric difference. Then it becomes a vector space over the field with two elements. And now there are two familiar orthogonal subspaces of this space, namely the subspace generated by edge sets of cycles in the graph, and the subspace consisting of the cuts of the graph. And to put that another way, if we look at the cycle space, this is exactly the things you can generate from the cycles using symmetric differences, or it's the space of things orthogonal to every cut. And it turns out, because this is over F2, it's enough to just consider disjoint unions of cycles to generate everything. Okay. If we move to infinite graphs, everything still works fine as long as the set X is required to be finite. Then this equivalence still holds. Of course, here, this symmetric difference, in order to be easily defined, is just a symmetric difference of finitely many cycles. And so that's kind of nice, but it doesn't tell us much about the infinite structure. Really, we would want to have something which tells us what's going on with infinite sets that we can build maybe as infinite symmetric differences of edge sets of cycles. And infinite symmetric differences, it's kind of clear, in some cases at least, how you should define the infinite symmetric difference of a collection of cycles. So in this guy, we have a collection of finite cycles given by all these squares along here. And if we take the symmetric difference of all these squares, it's clear which edges we should keep. These edges on the outside appear in just one cycle, so we should keep those. These vertical edges in the middle each appears in two cycles, so those should cancel, and we shouldn't take those edges, so we should be getting just this infinite set up here. Right, and the thing that made that work, the thing that allowed us to tell whether a particular edge should be in this infinite symmetric difference, was that each edge only appears in finitely many of the sets that we're trying to add up. And then we call such a collection of sets then thin, if each point is only in finitely many of them. And then to take the thin symmetric difference of such a family, we just take the set of all those points which appear in an odd number of things from the family. Okay, so now we can modify this result by taking, instead of ordinary symmetric differences, thin symmetric differences of edge sets of cycles. And it's no longer true that such thin symmetric differences will be orthogonal to every cut in the graph. For example, here I have a cut which just meets this red set in just a single edge. Right? That's an odd number of edges, so it's not orthogonal. But if you take a finite cut, then because all the symmetric differences are being calculated just on finitely many edges, you'll still have that any such symmetric difference is orthogonal to every finite cut. And the converse of this statement is also true. If you take a set of edges which is orthogonal to every finite cut, then you can find a thin family of finite cycles such that the thin symmetric difference of that family is equal to this set. This is not so obvious, and the proof of this fact uses two key facts about locally finite graphs, which we're going to be mirroring later on when we come to locally finite matroids. So I'd like to talk about this proof in a bit more detail. So the key fact that you need is the existence of so-called normal spanning trees in locally finite graphs. And a normal spanning tree is just a usual rooted spanning tree in a graph. So we have some tree order on this normal spanning tree, but in such a way that each of the edges of the graph goes between two vertices which are comparable in the tree order. So they can only go sort of up or down in the tree. You can't have an edge which goes across between two different branches. And you can build these normal spanning trees with a very standard inductive argument, so I don't want to go into the details of that. But the key point is first that they always exist, and second, which will be key for us, that all of the fundamental cuts are finite. What do I mean by fundamental cuts? Okay, there are two key kinds of objects associated to a spanning tree in a graph. Firstly, if I have an edge which does not lie in the tree, then the tree will include a unique path joining the two end vertices of the edge. And so together with the edge, that gives you a cycle in the graph. And this is called the fundamental cycle of that edge with respect to that tree. On the other hand, if I take an edge which is in the tree, then when I remove that edge, it divides the vertices of the tree up into two connected components, and then the cut going between those two components is called the fundamental cut of that edge with respect to the tree. And we have the following key equation, that an edge of the tree is in the fundamental cycle of an edge outside the tree if and only if the edge outside the tree is in the fundamental cut of the edge in the tree. This is easy to check. Okay. So now we have some set which is, let's say we have some set X, which is orthogonal to every finite cut in a graph. And we want to build this set out of finite cycles. Excuse me. So, right. There is now a simple formula for how we can do this. If we make use of some normal spanning tree T, we can simply write this set as a thin symmetric difference of all of the fundamental cycles of the edges which are in the set X, but not in the tree T. So, for example, in this graph, this path here gives a normal spanning tree. And you can see if we take the fundamental cycles of the edges of this set, which don't appear in the tree, those are then precisely these red cycles. And when you take the thin symmetric difference, you get back the set that you started with. Why is that true? Why, for example, do you not get this edge down here? Well, what's going on is if we look which edges contribute to the symmetric difference at this edge, that is, which edges have this edge on their fundamental cycle, those are going to be precisely the edges which lie on the fundamental cut of this edge, and also which lie in this set. But we're assuming that our set meets each fundamental cut in an even number of edges. And so here we get an even number of cycles contributing to this edge, since this edge itself wasn't in this set. And so that's why it cancels there. So let's work this out a little more formally. So it's clear that these sets coincide on the edges outside of T. So let's consider some edge F, which is an edge of our tree. And the set which interests us is then the set of those edges in X without T, which have this edge in their fundamental cycles. Right. But by the equation over there, that's just equal to the set of such edges that lie on the fundamental cut of the edge F. And so this is simply equal to the intersection of X with that fundamental cut, except, of course, that the edge F itself is not included because F is in the tree. Okay. And now, because this fundamental cut is finite, all these sets are finite, so we have a thin family. And because all these sets have even size, we get that this set has odd size precisely when the edge F is contained in the set X. And that's precisely what we need to get this equation here at the top. Okay. Good. So that gives us the equivalence between these two statements. And then we do also have another statement like the statement from before that these sets are disjoint unions of some kind of cycle. Yes?
Sorry, this theorem is only for locally finite graphs.
Oh, yes, this is for locally finite graphs. If I don't say so, you can assume in this talk that the graphs are locally finite. Okay. Right, thank you. So, yes. So I guess this isn't too surprising. We saw here that when you generate in this way, what you get is precisely a topological cycle. And this follows in a straightforward way from the fact that the topological cycles are precisely the minimal sets which appear as thin symmetric differences of edge sets of cycles, or which are orthogonal to every finite cut. That fact's a little harder to prove, so I won't discuss that today. But what we see here is that in addition to the topological characterization of topological cycles from earlier, we now have an algebraic characterization. They're the minimal sets which are thin symmetric differences of edge sets of cycles. Another thing that we might notice about this characterization of topological cycles as minimal sets orthogonal to every finite cut is that this is very reminiscent of how you might define the dual of a binary matroid, right? The cycles of the dual of a binary matroid are the minimal non-empty sets orthogonal to every circuit of the original matroid. And this is no coincidence because behind this dictum from Tutte that we saw yesterday, that if you have some statements about graphs which only refer to the edges and maybe to the cycles in the graph, then such statements are generally true for matroidal reasons. And it slowly became clear within topological infinite graph theory that the same thing was going on, that these statements which remain true for infinite graphs are often true for matroidal reasons. because the edge sets of these topological circles look like they should form the circuits of some infinite matroid on your set. But in order for that to make sense, you need a good notion of infinite matroids. And for a long time, it looked like there wouldn't be any sort of canonical notion of infinite matroids. And the problem is a very basic one. We know that there are many different cryptomorphic axiomatizations for finite matroids in terms of circuits, bases, independent sets, many other things. And it's the interplay between these different perspectives that makes the basic theory of finite matroids work so well. But if you take these axiomatizations and you just let the ground set become infinite, then they diverge wildly from one another. And you end up with very different classes of infinite objects. Now, there is a crude way to fix this, which is to impose some kind of finitariness condition. Maybe you take the circuit axioms and you say in addition that each circuit should be finite. Or you take the axioms for independent sets and you also say then that an infinite set should be independent as soon as all of its finite subsets are. And if you do this, then you can recover the equivalence between these cryptomorphic characterizations, and you can get a lot of the basic theory of finite matroids to generalize to these finitary matroids using compactness arguments. And at the time when this was first introduced, this seemed like a really neat thing. Compactness arguments were new, they were all the rage, and so it was nice that you could push all this through. But there was a big problem with this way of resolving the issue, and that is that you lose the duality. So it's very often the case that if you take a finitary matroid and you look what the dual ought to be, then you end up with circuits that should be infinite. So the dual would not be finitary anymore. And also, of course, this way of encoding things is completely unsuitable for the example I mentioned earlier, the topological cycle matroid of a locally finite infinite graph. Right. So Rado asked, I think in the 60s, whether it was possible to do a bit better, whether you could find some good notion of infinite matroid in which you preserve this powerful duality. And there were a lot of attempts to answer this question. Lots of different people suggested various definitions for infinite matroids, all of them fairly technical and based mostly on one of the axiomatizations or the other, maybe based on the axioms in terms of span, or of closed sets, or of independent sets. And because there were so many technical things competing with one another, it wasn't completely clear what the right choice was. So to the experts, to the people who really knew what they were doing, it was maybe a bit clearer. So Higgs introduced a notion that he called B-matroids, and he could see that this was really the right thing somehow. And Oxley also recognized this, and he even had a nice result which characterizes the class of all B-matroids as the largest class of pre-independent spaces closed under duality and minors. Okay, don't worry if you don't know what that means, but it means this is a very natural class of structures to consider. So it was kind of clear to these people that this was right, but because working with these things was very technical, they weren't able to convince the wider community that this was really the right thing. And the situation stayed like that for quite a while until, motivated by these ideas from topological infinite graph theory and from trying to find a notion of matroids that would include these examples, a team consisting of Henning Brun, Reinhard Distel, Matthias Krizel, Rudi Pendavingh, and Paul Wallen finally found a collection of cryptomorphic axiomatizations for infinite matroids, which correspond to the familiar axiomatizations for finite matroids. And these axiomatizations are mostly in this sort of style. You take, so these are the basis axioms, and here we take the usual basis axioms that are familiar from finite matroids, and then we have an extra axiom here, which in slogan form says, if you try to take a minor of this structure, then you will still have at least one base. Why does it say that? So if you're just given the bases, maybe seeing what happens if you contract an arbitrary set isn't completely trivial, but at least what happens if you contract an independent set is clear. Then you just take the old bases that included the independent set and throw that set away. And so if we contract some independent set I, and then we want to restrict onto some set X, what should we do? We should take the maximal independent sets. We should take the maximal sets, which are of the form some old base intersected with our set, where, of course, because we're contracting I should be a subset of our base. And if we have a maximal element here, then when we throw away the set I, we should get a base of this minor. Okay, so all of the axiomatizations are in this style. You take the axioms for finite matroids, maybe you tweak them a little bit so that they make sense on an infinite set, and then you add an extra axiom saying that you have bases in all minors. But the details of these axiomatizations won't be important for us for the rest of my talk. So don't worry if you didn't manage to completely memorize and understand these axioms in the last 2 minutes. Okay, so, right. So we've already seen a couple of examples of these infinite matroids. We've got the finite cycle matroid of a graph. In this one, all the cycles are finite, so this is even a finitary matroid. We've got the topological cycle matroid of a graph. They're the edge sets, the circuits are edge sets of these topological circles in the graph when we add the ends. And and these matroids here are always co-finitary. Their duals are always finitary. In fact, we can say precisely what the dual is. So the co-circuits of the topological cycle matroid are precisely the finite cuts of the graph. And for the finite cycle matroid, just as for ordinary graphs, the co-circuits are just the cuts of the graph. So what does this mean? Well, firstly, it means you can build the topological cycle matroid out of the finite cycle matroid in a very canonical way. You dualize, then you finiterize. That means you just take the set of all finite circuits, and then you dualize again, right? So this is the co-finiterization, and this says this topological cycle matroid is just the co-finiterization of the finite cycle matroid. What this also means is that this construction by a matroid duality adds to our topological and algebraic characterizations of the topological cycles in a graph, now also a combinatorial characterization through matroid duality. Okay. Right. Actually, I'll come to that in a minute. So, since the introduction of these axioms, the field of infinite matroid theory has really blossomed over the last few years. I'd say all of the basic theory of finite matroids is now also understood for infinite matroids. You have, of course, minors and duality and all of the basics. You have a notion of representability for infinite matroids, in which you use these kinds of infinite linear combinations, like the thin sums of sets that we saw earlier. You have a notion of graphic matroids represented now not necessarily in infinite graphs, but in topological spaces, which are somehow like graphs, such as these spaces that you get from graphs by adding these new ends at infinity. And for all these things, you have then the familiar characterizations through excluded minors that we know from finite matroid theory. And there are also some results which only start to become interesting as questions when you turn your attention to infinite matroids. Just as there are some statements about graphs, about infinite graphs, which are only really interesting for infinite graphs. So, for example, there's Harlin's theorem about collections of disjoint rays in infinite graphs, and we'll see a matroidal analog of that later today in Anne-Katrine's talk. Right. But what I want to talk about now is the restrictions that we need to put on, or the objects that we need to consider, if instead we want matroids which have the extra properties of locally finite graphs. For example, this property that the infinite circuits are just generated algebraically under thin sums from the finite circuits. And to see that that's not always the case for infinite matroids, we could consider another class of infinite matroids that we get from any locally finite graph, and these are the algebraic cycle matroids. So here, the circuits are given just by finite cycles in the graph, or by, again, edge sets of double rays. So double rays are just two-way infinite paths through the graph. And if you take a locally finite graph, this always gives you a B-matroid, and what's more, this B-matroid is always going to be co-finitary, just like the topological cycle matroid was. And now, let's think what happens if we just take some infinite tree. In this infinite tree, we have somewhere a double ray. So there is an infinite circuit. But because it's a tree, there's no finite circuit. So there's no hope of generating the infinite circuits from the finite circuits under any kind of sums. Right. So I think the right perspective to fix this and to see what's really going on in that example, or sorry, to what's going on in the case of locally finite graphs, is to say this statement about generation from finite cycles isn't just about one matroid. It's a statement about the relationship between two matroids, the finite cycle matroid of the graph and the topological cycle matroid of the graph. Now, we already saw that the topological cycle matroid is just given as the co-finiterization of the algebraic, of the finite cycle matroid of the graph. But we also have something in the reverse direction. The finite cycle matroid is just given as the finiterization of the topological cycle matroid of the graph. Remember, finiterization means you just take the collection of all finite circuits as your new circuits, and a finite topological circle is just a cycle in the graph. Okay. And so what I'm going to claim is that the proper context is simply a pair of matroids which are related to one another and constructible out of each other in this way. So I say a twinned pair of matroids is just a pair such that the first one is the finiterization of the second, and the second is the co-finiterization of the first. Okay. And now, in order to make the argument from earlier work, what we need is something corresponding to normal spanning trees for these structures. And the structure that we need is so-called normal bases. So these are sets which are bases for both of the matroids in the pair. Equivalently, that means you have a base for the first matroid of the pair, such that all of its fundamental cocircuits also work as fundamental cocircuits for the second matroid. So all its fundamental cocircuits are finite, which corresponds to this property of normal spanning trees in locally finite graphs that we saw before. And so the theorem which makes all of this work is that whenever you take any twinned pair of matroids, you can always find a normal base for that twinned pair. Right. So how can we argue for this? We would like to... No, before I start the argument, you can easily check that if you have a twinned pair of matroids, then the connected components of the first matroid are the same as those of the second matroid, because edges are in the same component if they're on a common circuit or cocircuit, so you can use that to go back and forth. So without loss of generality, we can assume that both matroids in our pair are connected. Okay. And now we would like to build a normal base. We'd like to build a set I, which is spanning with finite circuits, and the complement of which then co-spans back the set that we started with finite cocircuits. And the plan is to build now this base, together with its complement, recursively. So we're going to just put various elements into the base. We put those in some sets In, or into the complement. We put those in sets Jn. Of course, since we want to build a base, all the sets In should be independent, and all the sets Jn should be co-independent. And we want to make sure that if we ever put anything outside the base, then we span it from the base. And we look after that at the next step. Similarly, we want to make sure that if we put something into the base, then it's co-spanned by the complement of the base. And we'll look after that again at the next step. Right. So here, I said independent and co-independent and so on without specifying which of the two matroids I mean there. But because this is a finite set, this In, if it's not independent, it includes a circuit, and that circuit has to be finite. Right? So being independent for finite sets is the same for a matroid and its finiterization. So this is unambiguous between the two matroids here. And the same for this, and the same for spanned and co-spanned. Okay. And now we could ask, how do you make this recursive construction? I'll try that here. So let's say we've built so far some independent set In. And over here, we have some co-independent set Jn of edges. And now we would like to span one of these edges from this co-independent set at the next step. Well, because this set is co-independent, we know that for each of the edges, there is some circuit which meets this set precisely in that edge. And because it was unambiguous between the two matroids, we can assume this is a circuit of the finitary matroid. So we can assume this is finite. And now, the first idea would be to say, right, now we just throw in these finitely many more edges into In, we still have a finite set, and we span this edge. The problem is that this new set of edges, after we throw this in, might not be independent anymore. We might have picked up some circuits. So to get around that, we take within this set of edges, within this circuit, we take a minimal subset which, together with In, spans this edge. And because of the minimality, the union with this set will then be independent. We now do that for each of the elements of Jn. And with a dual argument, we expand Jn to things which co-span each of the elements of In. And so after finitely many such steps, we can achieve appropriate sets In plus 1 and Jn plus 1. OK. Now we take the unions of these sets. That gives us sets I and J. And you might think that here we're not done yet, because at each step we only had finitely many edges. So after countably many steps, we've only covered countably many of the edges of the ground set. And maybe now we have to keep arguing transfinitely to cover the remaining edges of the ground set. But the fact is that we've already covered the whole of the ground set. And that follows from the fact that I spans J, and J co-spans I. So if we take our matroid M, either MF or MC, it doesn't matter, and we contract the union of our sets I and J, well, since I spans J, that's the same as if we'd just contracted I and instead removed J. But now by a dual argument, since J co-spans I, that's the same as if we'd removed the union of I with J. And so this means that in this matroid, for the rest of the matroid, it doesn't matter whether we contract the set I union J or remove the set I union J. And that's equivalent, that's a standard characterization of when this set I union J is a union of connected components of the matroid. And so what this means is that what we've covered is a union of connected components, and we assumed at the start that the matroid was connected, and so we must have covered the whole of the ground set of the matroid already. OK. So that proves this statement. And then another thing which makes this sort of a not completely trivial statement is that these twinned pairs of matroids appear all over the place. So there's a very blunt strategy that you could use to try to build a twinned pair of matroids. You take any matroid, you finiterize it, and then you co-finiterize, and then you finiterize, and then you co-finiterize, finiterize, co-finiterize. You could hope eventually this stabilizes, right? And when you co-finiterize and finiterize, you get back to where you started. And the fact is, yes, this process always stabilizes, and always stabilizes very quickly after just 2 steps. So this, this is kind of a boring argument. You just look what has to happen and check the details. Anybody who's ever seen an argument with Galois connections already probably knows how this should go. So I won't talk about the details of this, but this says that twinned pairs of matroids are all over the place. They come up very often. Another nice thing about these twinned pairs of matroids is that it's natural to treat them as unified objects, in the sense that for almost all matroidal properties that you could think of, the property is true of the first matroid in the pair precisely when it's true of the second in the pair. For example, for any given field, the first matroid is representable over that field precisely when the second is. Or the first matroid is graphic precisely when the second is. Indeed, they have the same collection of finite minors. And also, perhaps I didn't mention this earlier, but there is a good theory of connectivity for infinite matroids. So if you have a partition of the ground set of an infinite matroid, and you want to know what the order of this partition should be, what you can do is the following. You take any base of the matroid, and you look how it crosses the partition. And maybe there's an edge on the right whose fundamental circuit goes over to the left. In that case, you can replace some edge on the left by one on the right, and still have a base which is moved a bit further to the right. And then maybe you can do this again, and again. And you look how long you can keep on doing this. So you look how far you can transfer this base across towards the right or towards the left. And the sum of these two values is always the same. It doesn't matter which base you start with or how you do these operations of transferring. This is a constant, and this is the order of this separation. If it's, of course, it might be that you can keep going forever, then you say the separation has infinite order. Right, now I said it doesn't matter which base you take here. So you could take a normal base here. And then that normal base is a base for both matroids in the pair. And so what this means is that also the orders of separations are unambiguous between the two matroids. Okay, so you can treat these as unified objects. And I claim these objects look very locally finite. Why is that? So first, it follows from the proof that we had earlier. If you have a connected twinned pair of matroids, you cover the whole ground set in countably many steps, it must be countable, right? Just as any connected locally finite graph is countable. Similarly, if you have a connected twinned pair of matroids, you get a distance function on the edges of that matroid. So to define this, first we consider a fixed normal base, and now we look at the length of chains between edges where you just travel along fundamental circuits for this base. Okay, so that will give you, with respect to this base, a distance between any two edges. But in fact, for any two edges, there's also a strict upper bound, which means that if you take the supremum over all normal bases of the distance through the base, so formally through the bipartite graph defined by the base with respect to the relation of containment in the fundamental circuits and co-circuits, then this gives you a distance function on the matroid. And the number of edges within a distance d from a given edge will then always be finite. So this distance function gives you a very good grasp of the global structure of this twinned pair of matroids. Thirdly, we shouldn't expect minors of twinned pairs of matroids in general to be twinned pairs of matroids, just as minors of locally finite graphs aren't always locally finite. But if you contract or delete only finitely many edges in a twinned pair, then you still have a twinned pair of matroids. And what's more, if you started with a connected twinned pair, then when you contract and delete finitely much stuff, it only falls apart into finitely many parts. So all of this looks very locally finite. And yes. So there are some fairly straightforward-looking questions about these twinned pairs of matroids, which I'm completely baffled by, and I wanted to tell you about one of these. What I've tried to do, I've tried to take this question and boil it down into its most elementary form that I could for you. So even if you've understood nothing in my talk, even if you don't know what a matroid is, this question should still make sense. It's a question about matroids which lie between the two matroids of a twinned pair. And here I've taken the twinned pair given by the finite cycle matroid and the topological cycle matroid in the infinite grid. So we have a set curly C sub f. This is the edge set, a set of edge sets of finite cycles in this grid. So those are the cycles of the finitary guy. And then for the cofinitary guy, we've got the set of, not yet, we've got the set of finite co-circuits the set of co-circuits of the cofinitary guy. Those are, of course, bonds. There's minimal non-empty cuts. in the dual, so those are the circuits of the dual matroid to the topological cycle matroid for this graph. And those are just the finite cycles in the dual graph to this graph, which is again an infinite grid. So these two sets are somehow symmetric with one another. And now we take a matroid between these two, which will be specified in terms of its set curly C of circuits and its set curly D of co-circuits. And we want that C includes all the finite circuits, D includes all the finite co-circuits, and we want them to be anti-chains of non-empty sets so that they satisfy the first and second circuit axioms. And we want them to be orthogonal to one another. So we want that any intersection of a circuit with a co-circuit has even size, and in particular has finite size. And now what I claim is that there are precisely two options. Either C was equal to CF or D was equal to DF. So there's no matroid strictly between these two, is what I'm claiming here. And the reason why I really believe this should be true is that this statement certainly follows from the so-called infinite matroid intersection conjecture, or packing covering conjecture. So this is a statement that gives a common unifying generalization of the packing, covering, intersection, and union theorems for finite matroids. It puts them all together in one symmetric package. And it also gives a kind of a matroidal version of the Aharoni-Berger theorem, which is kind of an infinite version of Menger's theorem. So I'd say this conjecture is one of the, well, probably it is the deepest and most interesting open problem in infinite matroid theory at the moment. And it reaches its tendrils across into this kind of a question. So if any of you have any ideas about how to attack this question, then please do come and talk to me. Let me know what you think. OK. Thank you very much.
All right. Thank you, Nathan. Are there any questions?
Yes. You talked about the B-matroid and the modernization of it as
Yes.
Pendavingh and Zwam and others. That theory should associate with an infinite graph a unique infinite matroid, I suspect. Is that it? And you're saying it's the co-finitized.
Ah, OK. So this is, can I comment on that first?
Okay.
Because maybe it affects what you want to say in a moment. So first, the question is, should there be a unique matroid associated to an infinite graph? And I would say that the answer to that is no. Because for infinite graphic matroids, which you can express in terms of excluded minors in the usual way, there is a theory of representations, not over graphs, but as I said, over these topological graph-like spaces. And I would say that what happens instead is that for each graph-like space, you can get, at most, a unique matroid associated to that space. But associated to any graph, you can build many graph-like spaces. Right? You could just take the geometric realization, then you get the finite cycle matroid.
I was suggesting there should be a unique matroid associated, but I was saying there should be a unique matroid associated via the definition of the modernized definition of a B-matroid.
Ah, no.
Well, let me finish that.
OK.
But, I mean, you're saying that the two pairs, the twin pairs, is a more natural concept.
Yes.
And I think that should say that there should be a twin pair of matroid, B-matroid concepts. That is, that these should be regarded as two different theories, and it would be interesting to have the other B-matroid concept available as
Okay. So the question is, how should this look if we know that we have these twinned pairs and these are naturally associated
What's happening there?
to graphs? Yeah. Should it be that there's a twinned pair of B-matroid concepts?
Yeah.
Right. So what I would say is, so first of all, I would say you get many matroids associated to a graph coming through these many topological spaces that you can associate to a graph, but you get just one twinned pair of matroids associated to a locally finite graph. So that is unique and canonical. But also this notion of twinned pair, I would say, looks like a unified thing in itself, right? It's self-dual. So if you take the dual of it, you don't get a different notion. And it's closed under the minors you would hope for locally finite structures. And so I wouldn't expect to get a second notion of B-matroid, which is twinned to the original. Instead, I would say the original notion of B-matroid enters in a twinned way with itself into the definition that we made of twinned pairs of matroids. Right? Here. We've got here two different B-matroids which are twinned with each other.
Are there any other questions?
I have one question about this packing coupling conjecture.
Yes.
So you now have this theory of twin pairs of matroids. I mean, one is finitary, the other co-finitary, and they both obviously satisfy the packing coupling conjecture.
Yes.
Could you now use your techniques to say something about the matroids in between?
Well, yeah. So as I said, if you no, okay. If you want to say something about the matroids in between, I mentioned at the end that you have this that this final problem follows from the packing covering conjecture, but it follows from packing covering for two matroids, one of which is finitary and the other of which is co-finitary, right? And this is the case in which we don't have a good argument.
Yeah, I mean, this is nice and clear to me, but I mean, do you get some new instances where packing covering is true for matroids that sit in between, kind of using the fact that it sits in between?
I think what you would need for that is a stronger statement, which is, so there is a kind of a stronger statement that you can see as a kind of a packing covering statement for these twinned pairs of matroids. Sorry, probably people are not knowing what packing covering and so on is about. So, so a base packing in a matroid is just a pair of disjoint bases. A base covering is just a covering of the whole ground set with two bases. And packing covering says that you can find a partition of the ground set into two parts, such that when you restrict onto one part, you get a base packing, and when you contract onto the other part, you get a base covering. And now, if these are twinned pairs of matroids, it would be natural to say, in this packing, the sets shouldn't just be independent, but they should be independent in the stronger sense, right? They should be independent in the co-finitary. No, wait, independent in the stronger sense? In the finitary matroid. And then for the other one, for the covering, again, in the matroid which makes the statement as strong as possible, which I think in that case is the finitary one. Right, and then packing covering would be the same statement, but where you interpret packing and covering in the two different matroids to make it as strong as possible. I think this should also still be true, and then that statement would give you packing covering type results for the matroids in between.